Hi, so I said I'd put together a little video addressing question 49. Thought it was quite an interesting one. So just try to zoom in on this as best I can. So we've got our refractive index. Sorry, the question goes, let me address the question itself first. Use trigonometry to show that the refractive indices, the refractive index between two media is equal to the ratio of the wave speeds v1 over v2 in the media. And then part B says show that the refractive index for the waves going from medium 1 into medium 2 is given by 1n2 or n2 over n1. So let's just pull up the simulation here just to get the ball rolling on this thing. So we've got our two materials, and the first one is air and the other one is water or glass or something like that. So I'm just going to change view here from the ray model that we're used to, and I'm going to put in the wave model. And on the simulation there's a way of slowing it down a little bit as well, so we can see the waves as they kind of propagate through both materials. I'm just going to try to zoom in here as best I can, and then I'm just going to move away from it. So you might be able to see that as the wavefront moves in, the left-hand side of the wave strikes the material first. That bit gets slowed down, and it essentially turns the entire wave. But the bit that I really want you to pay attention to is that if you look really closely at it, you'll see that the wave, the point where the wave is going through air and through the water at the same time, they never lose contact throughout throughout that time when they're moving from air into water. So it starts to on the left hand side, if you just kind of follow it across there, they're always in contact as they move the way across. Okay, why is he talking about that? Okay, so just before I get going there, I have two different screenshots of the wave, just to really highlight that point as the wave moves through the air above here. The wave fronts here never lose contact with the wave fronts here. They're always in contact as they move along, okay? And this is another one. And again, you see the yellow dots represent those points of contact between at the wave boundary, at the boundary of the two medium. So the yellow dots are, if you notice, they're evenly spaced on the right hand side and on the left hand side. Okay, and we're going to use that in our derivation. Okay, so I've sketched medium 1, which is the air. It doesn't really make a difference what medium it is. Medium 2, we'll just pretend it's glass or something like that. I'll switch color here just so we can see. I'll highlight as we go. So you can see then that the incident ray is coming in like this. It strikes the medium 2, so it's moving through medium 1, strikes medium 2 surface, is refracted, is bent towards the normal here, and continues on its way. So that means that the angle of refraction, I'll just highlight that here, that's the angle of refraction I. I'm just going to use I and R for this instead of theta 1 and theta 2. It's just handier, I think. And the refracted angle is down here, R. Now, by a little bit of trigonometry, I can tell that if that's the if that's the incident angle, this is the incident angle as well, obviously. We've got 90 degrees here, and I've got my wavefront is drawn perpendicular to my incident ray. So it turns out that this one has to be the incident angle as well, okay? And by the same token, or by the same logic, again, the wavefront is drawn at 90 degrees to the refracted ray, then this one is also the refracted angle. Okay, so the refracted angle is here and here, and you can see the two angles are pretty much the same anyway. Now, what I've tried to show in the picture here is that when the wave is moving through the air, or whatever material 1 is out here, the waves are pretty much spaced out. Okay, they're fairly well spaced out. So we've got one wavelength, and I'll call that lambda 1 on the upside, or sorry, on the upside of the glass, if you like. Can't think of the word. So we're moving along in wavelengths, and each wave front is showing the distance of one wavelength. Okay, so the next wavelength would be here. Okay, now it's at this point that I've drawn this one fairly specifically at the normal point. This one has already hit the glass. It's half of it is kind of rotated in, and it's now after slowing down inside this material. And you can see that quite obviously because the wavelength, the distance that it travels in the same amount of time, is a bit slower. It's a bit, it's not as much. Okay, so we're down to lambda 2. Now, the logic that I'm trying to use here to try to prove this, what I'm doing here is I'm going to use a certain distance x, and it's basically going to be the distance between those yellow dots that we had in the previous diagram. So these distances are all the same. So that means this is x and this is x. And this one here is defined, this x, I've got a theta I, or sorry, I've got a angle of incidence I, and I've got a lambda 1 up here. And so I've got one triangle here and an angle of incidence, and I've got another triangle down here that's got an angle of refraction and a lambda 2, which is down here. Okay, so that's the plan. I'm going to try to equate these two quantities and just see what comes out of it. So I've just zoomed in on the top portion of it there, on that top part of the triangle. Again, I've got my x, my lambda 1, and my angle of incidence, which is here. And I know that this is one wavelength when it's traveling in material 1. Okay, and I've kind of cut off material 2 there. I'm just going to sort this bit out first. So I know that if I was to take the sine of the angle of incidence, then that would be the side opposite divided by the hypotenuse. Well, the side opposite this is lambda 1, and the hypotenuse just so happens to be this value x that we've marked on both sides of it. So then if I just drop the middle part, and sine I is going to be lambda 1 over x. I'm just going to rearrange that quickly. For x, it's going to be lambda 1 over the sine of the angle of incidence. I'm going to do the exact same thing now for the other side. So this is the lower half of the triangle. This is the refracted ray coming out, and we've got lambda 2 here. I've got my refracted angle here, and notice here is that x. So again, I'm just going to try to equate those two. So again, I'm going to take the sine of the angle of refraction, which is also the opposite over the hypotenuse. The opposite to that one is lambda 2. And again, the hypotenuse turns out to be x, because the hypotenuse is on this side of it, the right angle being down here. So that means that x here is equal to lambda 2 over sine of the angle of refraction. So you can probably see where I'm going with this now. So now what I'm going to do is I'm going to equate the two quantities. Okay, so when I equate the two quantities, because they're both equal to x, that gives me lambda 1 over sine I equal to lambda 2 over sine of the angle of refraction. And of course, if you just do a tiny bit of algebra to that, you'll get it into a very, very recognizable form, which will be the first wavelength divided by the second wavelength equal to the sine of the angle of incidence divided by the sine of the angle of refraction. Now, of course, we all know that the sine I over sine R is the refractive index of that material 2 anyway. But just for completeness sake, what they wanted it was in terms of the velocities. So we know that velocity 1 is going to be the frequency times lambda 1, okay? So the frequency times lambda 1, bear in mind, it's the frequency. The frequency never changes. That is only dictated by the source and not the medium. So it's only the wave and the wave speed that can actually change. Wave speed number 2 is going to be that same frequency multiplied by lambda 2. And of course, if you were to divide these two equations by one another, then the frequency parts would cancel out, and you'd be left with velocity 1 divided by velocity 2 equal to lambda 1 over lambda 2. And that's basically what we've got. So I've got the whole thing now. Sine I over sine r, which is the refractive index of the material, is equal to lambda 1 over lambda 2, ratio of the wavelengths, which is equal to the velocities, the ratio of the velocities. This is the bit they wanted us to prove. And for the last part, I think they asked us for the ratios of the two refractive indices. And that's basically what it is anyway. Okay, so hopefully that makes a bit of sense to you. You can spend a bit of time going through that. Make sure you understand how I managed to do that derivation, and you can have an idea about the geometry of it. Okay.